Oh my god. Dude, I've been talking for 30 minutes and none of it has had audio. Oh my god. Ah. That's so sad, dude. I've been looking at like my microphone light and that's been on and that's been acting normal, but I forgot to look at OBS itself, dude. Oh, it's so tragic. Oh my god. Thank you. Okay. Oh, Jesus Christ. Okay. I'm so upset. Okay. Did OBS reset the mic? I have no idea, to be honest. I have no idea. I just had to change it from I just changed the properties from what's it called? Whatever the default was. I guess the default was not correct. Okay. Man. Man. That sucks. Alright, let's try to reset this explanation then. A little bit. This is gonna be a little scuffed. It's minorly scuffed, but it's okay. We're alright. We'll be okay. Oh, that's cool. That's another solution. Cool. Alright, where are we? So let's put this back to 0. Let's take this off. Let's take this label off. Let's take this off. Oh, that's so tragic. That's half an hour of explaining. Just out. Alright. Let's reset. Let's reset a little bit. Just a little bit. I'm not gonna go as deep into it, but it's okay. Let's erase all this. Erase all this. Okay. Let's actually get just another. I still could use this. It's fine. When OBS sometimes updates, it sometimes resets the micro device to default. So if you use non-default, you have to manually select. Yeah, that's just a tragic way to learn my lesson. So in the future, I won't do that. I won't make that mistake again. I hope. All right, let's get a coordinate grid going. Let's get a nice long grid. No, I don't like this app very much. It is convenient because it's already installed on my computer, but I'm not a fan of this Microsoft Whiteboard app. I don't know. There are some things that don't make sense to me. Like it automatically choosing to convert things to shapes. It happens to you all the time. Yeah. Yeah, it's okay. We'll figure it out. All right, so then let's get this one. I just want a nice little like coordinate grid. Is that too much? Can I just get some axes? I don't want. Listen, I just want to edit this. Thank you, thank you. There we go. All right. There's got to be some better tools for drafting this stuff. Why is hitting escape get me the Windows search? That's weird. I'm hitting escape, not the Windows button. Oh well. Okay. So we've got our Y, we've got our X. Whoa. Okay. Why are we glitching out now? We've got our X. Okay. So let's do a quick recap. Here's our goal, right? I want to be able to hold this board. This is not the actual board. Okay, this is from a different project. I haven't even thought about putting this on an actual board yet. But I want to hold this board, right? And somewhere in the room, there's going to be a clap sound or a supersonic sound, some specific sound, some big spike. And I want this device to be able to tell me where that came from. And so I'm trying to basically recreate echolocation. All right, we're trying to do some good old-fashioned echolocation. All right. And so The idea is that if I have a microphone right here, we're going to put a microphone right smack dab in here. Mic 1. This is going to have some x value, right? X1, and it's going to have some y value, y1. In this example, it's going to be 0, 0, but you know, it's it could be generalized. It could be any point. Okay, so let's say, for example, that I know the clap is happening at time 0. Time 0. This is when the clap happens. Time of clap, or time of speaker, right? Because this will probably be a speaker. I'm a one-man show. So this is the time of the speaker. And so let's say that the mic picks it up, right? T1, mic 1 picks up at 1 second. All right, well, we know that the speed of sound in air, the speed of sound is called c. It's usually denoted with c. Why is this still purple? Hello? Guys? Why is this not black? It should be... Okay, this is blue. All right. C in air, the speed of sound in air is 346 meters per second. Okay, so that tells me now, if I multiply 346 times 1, that tells me that the speaker then has to be, right, using this as well, that tells me that it has to be 346 meters away from the microphone. All right. And thanks to the magic of modern computing power, we can actually do this much faster. We can get this down to like, you know, 0.1 seconds, 0.01 seconds, and we can get pretty accurate with our distances. Okay, so let's take this and put this up here. We'll just keep that at the top. Keep it looking pretty. It's pretty important. All right, so now that we know that our microphone, or sorry, our speaker is 346 meters away, that could be over here, right? This could be a speaker. It could also happen, that was 1, 2, 3, 4, 5, 6 blocks. 1, 2, 3, 4, 5, 6 blocks. It could also be over here. It could also be over here. Sorry. Over here. Not there. Was off by 1. It could also be over here. It could also be over here, and over here, or over here, or over here. All of these are possible points. And so what we'll end up with is, based on this information, we can get a circle. This is not a coincidence. This is just the definition of a circle. Very convenient, very beautiful. All right. I can actually get a circle over here. Let's make it a nice little purple circle. I don't want any text on it. Center it on this, and then expand it out. Something like this. Oy. This is difficult. All right, something like this. Is this not a circle anymore? Anyway, I'm not gonna, you know what? We're not gonna get into it. We're just gonna move on. Move on. Okay, so all of these are possible points of the speaker. Okay? And it's not very nice because now I'm stuck with all of these possible solutions. So all I have to do is I add a second microphone. I don't like that. All right, second microphone. Don't like that at all. Okay. The second microphone has its own x value and its own y value. X2, comma, y2. All right. And so the speaker is going to hit this at time 1. The speaker is, the clap is also going to hit this at time, some other time, right? Time T2 is equal to like maybe 1.1 seconds. And so now if we follow the same process, we'll actually get another circle. We'll get another circle centered around microphone 2. But this circle is actually going to be bigger because it took longer. So that means that the speaker has to be further away from microphone 2. It's going to be a little bit bigger. So all of these in black are possible solutions for where the speaker could have been, and all these in purple are where the possible solutions for the first microphone could be. The speaker is in relation to the first microphone. And we know that both of these are true because these are the same clap. And so these are possible points. I actually want this in blue. So these are possible points for the speaker, right? Where they connect are possible solutions, right? These are what are called solutions to our system of circles. To our system, meaning we just have multiple circles, and we're trying to figure out where they intersect. So now I've narrowed it down to actually 2 places. I've narrowed it down to just 2 locations where the speaker can be. If I add a third circle, this is going to be microphone 3. Come on. This right here is going to be microphone 3. Make another circle. Nope, I want it. Come on. I want this black circle without all of... Oh my gosh, I'm not enjoying this. Maybe I should just use paint.net or something. Oh my gosh, what is all this? I don't even know what all this... Like, I didn't want all of it. I just wanted the circle. All right, so let's center it around microphone 3. I guess that's impossible. That doesn't make sense. Why is that impossible? Because now what I'm looking for is a solution of all 3 circles. So this would have to be further away, I guess, from the speaker. If this is the speaker, it does this and this. How does that make sense? Ah, shoot. Maybe I'm lost in the sauce now. Let's take a look. How did this work? So you have the first circle, then you have the second circle, and the third circle. And these are all colliding. Process repeated for beacons 2 and 3, which yield 2 more circles. The target lies at the intersection of 3 circles. I think I gotta look more into this. Because I was expecting that this would end up like this. Right, where we have the intersection of 3 circles. The intersection of all 3 circles, and that would tell me where the microphone is. And maybe that is true. I guess I just have to be more consistent with how I draw my circles and be more programmatic about it. Because if I just randomly draw circles, the chances of me getting the radii correct is probably not good. Okay. Where was I? So this is what's called time of arrival. This whole system, this whole method is called time of arrival. Because we already know, this is known. And that's a pretty big deal to have that be known. And so this is called time of arrival. Ideally, in my little prototype, ideally, I would not know actually when the speaker plays or when the clap is happening. Ideally, I would just hear it and figure it out from there. Right? Similarly to how our ears work, we don't know when a sound is happening. We just know that a sound played. Okay, so what I'm looking for instead is this is not what I want. I want time difference of arrival. Okay, So rather than relying on these circles to figure out possible locations of the speaker, I'm only going to look at the difference in time it takes to reach one speaker compared to the other. All right? And so if I look at over here, I've got two microphones. Boop. Two microphones. And I've got a speaker. All right? So the speaker is going to hit microphone 1 at sometime 7. I don't know. Again, I don't know when the speaker played. Right? It hits microphone 1 at time 7. Then a second later, it's going to hit it at time 8. Okay? Time 8. So that tells me that the speaker has to be 1 second closer, 1 second of the speed of sound, 1 sound second, I guess. 1 second closer to the microphone, the first microphone, compared to the second microphone. Right? And so that leaves this location. Right? This is pretty nice. This is 2 blocks away from the first microphone, and this is 3 blocks away from the second microphone. That's a difference of 1. Okay. That's a good solution. But is that the only solution? Well, let's figure it out. So I know I'm trying to find the distance between mic 1 and the speaker. The distance between mic 1 and the speaker, we can use Pythagorean theorem. Right? This would be where the speaker can be. This is the first microphone. We take the difference of those because I'm looking for the difference in the x and then the difference in the y. We square those, add them together, and we get a. Right? And we get, sorry, this should be a radius of 2 squared. 2 squared. No, not 2 squared. Is it not 2 squared? Oh, no, it's not 2 squared because I already have this square root. Oops. All right, so it's going to look like this. Right? So this is the distance of mic 1 being 2. The distance when mic 1 is 3, when mic 2 is 3 units away. Oh, boy. Oh, boy. We're getting a little lost in the sauce now. All right, we're 2 blocks away from mic 1. We're 3 blocks away from mic 2. And so now I want to know, if I just take the difference of those distances, where are all of the places that the difference is only 1 second? Turns out there's a whole lot of solutions. There's a whole lot of solutions. And it's kind of a weird shape. It kind of looks like a sideways parabola. Kind of looks like a sideways parabola, right? And so, okay, let's take a look. So here I've got, this is the distance. This is a circle showing all the distances between the speaker and the microphone. This is a circle showing all the distances from the speaker and the second microphone. If I look at the difference of these circles, the difference here is only 1 block. So that's what I'm looking for. And if I move this speaker along this red line, you'll notice that the circles change. The circles change their radius. They get bigger or they get smaller. But that difference stays pretty consistent. I'm not very smooth with it because I'm not a robot, right? But the difference is pretty consistent. Mimeanwhile, if I stray away from that red line, right, the circles still change size and they still match up, right? The speaker still matches up with mic 2. This still matches up with mic 1. They still match up, but the difference is getting bigger and smaller compared to over here, where the difference stayed pretty consistent. Okay. So this shape, where this is true, right? This shape tells me, this red line tells me all the centers of my circles. And this is called a hyperbola. Solving a hyperbola, trying to figure out what the hell, like how do I even solve x and y over here? I don't even know. I'm not even sure. Right? It's not that easy. You might also notice, hey, wait. that's still, you know, uh, what's it called? What am I thinking? You might still notice that, hey, this is a whole bunch of solutions for where the speaker could be. How do I pick just one? You can't. So you actually do need a third microphone. Let's add in a third microphone. X3, comma, Y3. Let's make some sliders for this. Let's bring it up next to its brothers. Bam. Bam. Okay. And let's change the color. Options. Change the color to like green. All right. Okay. So this is mic 3. I got to go through the same process with mic 1 and mic 3, find the difference between those. Then I got to find the difference between mic 3 and mic 2 and end up with 3 different hyperbolas that are all going to line up. Don't mean to derail the topic, but I think there's some form of Windows Ink app or something where you can draw over a current screen if you want to draw over Desmos for a clean graph. Let's find that out. Windows Ink. Use pen menu in Windows. I could do a full screen snip. That is true, but I don't know how to do that. But like I don't think that's what I'm looking for because I want it to be more interactive where like my tablet lets me draw over it, but the mouse lets me interact with the website as normal. You know what I'm saying? Why is it not letting me go back? Displays. Okay. Draw over current screen Windows. I'll look into this later. There might be a live form of it. I'm not sure. Might be a live form of it. But anyway, let's figure out the. So first of all, let's draw a third circle. This one's gonna be. Let's actually change this. This one should match mic 1. So we'll make that blue. We'll make this one red to match mic 2. And then this one is going to be the exact same. However, instead of x2, it's going to be 3. Okay, and this is just the distance from the speaker to mic 3. All right, and so, look at that. That's beautiful. I don't want to look at my CPU usage right now, but look at that. That's beautiful. Okay. And so now I need to know how long did it take? What's the difference in time, right? Because this radius between the green and the blue, this changes all over the place, even along this hyperbola, right? The red and the blue, they stay pretty consistently far away from each other. But the blue and the green, right? Like, look, they even touch at some point and overlap and then change distances again. Right? So I want to figure out where are the blue and the green consistent? Where are the red and the green consistent? And so we got to draw more hyperbolas. So let's define a new variable c. That's going to be, let's say it takes, I don't know. Let's say it takes 5 seconds to reach, right? Here we have 0 to 10, step of 1, step of 0.1. Okay. And so let's draw a new hyperbola. Bam. We're looking for the difference between, so A is mic 1 minus C is mic 3, the third mic, the new one. And then we're going to just copy paste this. Bam. Copy paste that. So we have mic 1. This time we want mic 3. Mic 3. Okay. Why is this one not? Oh, this one's. Why is this not giving me a solution? So first, let's turn this off. Second of all, let's change this color to a dashed line. Let's change this also to a dashed line. This one, let's change it to green, I guess. But why is this not giving me a solution? We can turn this off. A minus C. Oh, this is negative. No. We did A minus B, and that was -1. A minus C is +2. So what the hell? Does this need to be like 9 for me to get solutions? Why is this not giving me solutions? Minus x3, y3. Yep. Why don't you give me solutions? What if I just do this manually, right? -2. Will I get solutions then? No? Oh, there were no solutions. That's why. There were no solutions. Okay, I'm understanding. So here, there are no circles where we can have a difference. Okay, so I'll be honest, this is where my understanding is starting to, this is the limits of my understanding currently. So I'm trying to figure this out too. Okay, so if the microphone is here, then that tells me there is no possible place where the difference in distances between these two will be 2. And I think that makes sense because the difference in these distances is not even 2. So I need this to be a little bit longer. Right? As soon as... Okay, the difference in distances between these mics has to be comparable, right? Like it has to be more than 2 as well. Okay, so I need to put this like, let's put this like over here. I think that'll avoid problems. Put mic 3 on 5, 4. Okay. All right. So now we've got these two hyperbolas. All right, and if I move the speaker, let's actually ignore the red right now. So if I move this speaker, right now I'm only looking at the red circle and the green circle. So let's take away the blue circle right now. If I move this, the difference in the gap, that gap between the red and the green starts to change. But if I move along here, nope, wrong one. Sorry, I need the blue. We're looking at the blue and the green, not the red and the green. Here, the gap between the blue and the green starts to change if I stray away from the green line. But if I stay on it, the size changes, but the difference seems to stay pretty consistent. Okay. All right, cool. So let's bring this back over here. And so now we need to look for over here. This is, all right, here the green and the blue change distances, but the red and the blue, mic 1 and mic 2, these will be consistent. So it needs to be over here. And so this is our solution. This is where the speaker would have to be. Yeah? Wherever this point is. Now, how the hell do I solve an equation like this? How the hell do I solve a system of equations like this? Also, I should change this to A minus C again. It should still be A minus C. Okay, let's, for completeness sake, let's draw the last hyperbola. And in theory, the last hyperbola should also have the same solution. So here we're going to look at B minus C. And we're going to have x2 minus y2. Compare that to x. Yeah, there we are. Look at that. Look at that. Okay, so by necessity, the solution of these two hyperbolas has to be the same as the solution between these two hyperbolas. Okay. And let's turn these off for now, and let's only look at green and red. Green and red. So if I stay along here, that doesn't seem right. Is that right? Oh, I guess that is right, huh? Cool. Yeah, notice how like this circle, the red circle is always at 5, and the green circle seems to always be at 6, as long as I stay along here. Until I get to here. But here, you know, the difference in distances is still, what is b minus c? -1. All right, yeah. Cool. Technically, I think hyperbolas are actually 2 branches. I think technically they're 2 branches. So I think this is supposed to be like absolute value here. No. I think technically it's supposed to, because it's supposed to be like one this way and then one like along here. Assuming that I'm okay with, like here I have the green on the outside and the red on the inside. But if I'm okay with having the red on the outside and the green on the inside, I should have a second branch, which should look like this maybe? No. I'll just have to take this, copy paste it, except with C minus B. And you should, yeah, there we go. Yeah, so these are hyperbolas. Okay, so let's get rid of that. All right. We're clocking in at an hour. My brain is already frying. Oh boy. Not a good omen. Oh, maybe I should get some food. But we're okay. Let's keep going. Okay. So that means I need to go along here. The difference between this circle and this circle is 2. And it stays 2. The difference between the red circle and the blue circle stays 1. The difference between the... I think I should change some of these. I should change this. This should be blue, and this should be green. Then the difference between the green circle and the red circle stays as -1. Okay. So this is where the speaker has to be. So there is only one solution. Now, how do I solve this? Because even on Desmos, if I try, normally if I have a function, I can click on the points, right? Like you can click on these points and it can calculate them out for you. But on this, it's not doing that. So I've got to go digging to see how to find the intersection of 2 hyperbola. Based on line equations. So this is the way I'm formatting my hyperbola. And now we do research. Now we turn into a study stream. So they're visualizing contour lines of a hyperboloid, which I think is like 2 cones stacked on top of each other. Okay. A quadric surface defined as a 0 set of polynomial degree 2 in 3 variables. I can also look through, maybe it's time to read through this Wikipedia article to see if they have any ideas. And it might be time to go back to, 9th grade geometry or 10th grade geometry or whatever, whenever I learned about these originally. and figure out what I'm actually looking at. Hey, look at that. We re-derived a hyperbola. Besides being a conic section, a hyperbola can arise as the locus of points, so the set of all points, whose difference of distances to two fixed foci or two fixed microphones is constant. As a curve for each point of which the rays of two fixed foci are reflections across the tangent line at that point, as a solution of certain bivariate quadratic equations. Cool. Line. Two asymptotes. Okay, so here is the definition of hyperbola, where the hyperbola is a set of points. We're going to call all those points h. It's equal to all of the points p, so this is the point p, such that the distance, the absolute value of the distance from the point to f2, that's our second foci, minus the distance from p to the other foci is exactly 2 times a. So the difference from p to f1, the difference from p to f2 minus this distance, so chop that off, it's exactly equal to from this point to this point. All right, cool. I'm accidentally re-deriving ancient Greek mathematics. It's crazy to me that like people were able to think about these things without such a powerful tool like Desmos. Like with Desmos, I can relatively easily physically see what I'm imagining. But back in the day, I mean, you just suffer. Where's the solution at? Back in the day, you just have to use your raw imagination, and that's beautiful to me. That is beautiful to me. All right. Applications. Multilateration. The task of locating a point from the differences in its distances. Yep. Lauren, okay, so maybe I should look into GPS and how GPS works. Some of those equations. Okay. Multilateration. Let's look at this. They discuss the methods, but they don't discuss much of the calculations. Because an Arduino is not. An Arduino is not that powerful. But also, I think GPS is a combination. Like, I think GPS also includes the time of arrival. Like, I think that's part of the packet. Is it says, this is my current time, this is my position, right? Principles. Very stable atomic clocks that are synchronized with one another and synchronized with the ground control stations. Any drift is corrected regularly. Yeah, okay. So their clocks are synced. So part of the packet I get, I think part of the GPS packet would include, yeah. All right. Each GPS satellite continuously broadcasts a signal that includes a pseudo random code, and then time of arrival can be found in the receiver clock, and it includes a message that includes a time of transmission. So you can, that's part of your packet, is to include it, so that way you don't have to just raw solve for hyperbolas. So maybe there are two thoughts I have. A, this is way out of my depth to solve for hyperbolas. B, this is me pushing the limits to the cutting edge. And this is, if I want to be, you know, if I'm trying to become Spider Man, I need to be able to think deeply about these things and be able to solve them. All right, let's see. Two hyperbolas given this form. Let's, you know what? Before we do this, let's try actually solving it. Right? Let's all of this stuff. All of this stuff. Let's just delete it. Delete. Delete. All right. Let's scrap all that. All right. Let's go and try to write it out. No, I just want a blank canvas. I don't want a mood board, bro. Like, when am I gonna do this for a mood board? Cause and effect. I mean, I guess they're trying to compete with companies like Lucid Chart and things for all that. Let me not show this for new whiteboards. I just want whiteboards. And if I want a template, I'll get a template. Right? Like I can just format the background. I think, how do I actually get? There are ways to get templates, right? Yeah, I can just click that button if I actually want a template. All right. Let's do white rule. Let's try to figure this out. Okay. So, did this turn off? Okay. Let's start with what's known. Things that are known. We have the positions of mic 1, mic 2, mic 3. And so by extension, we have x1, y1, we have x2, y2, we have x3, y3. We also know the times relative to each other. All right, so we know the distances from 1 to 2, distance from 2 to 3, distance from 1 to 3. We also know what was it? Difference in time. T1 minus T2. I guess we could just call them T1, T2, T3. T1, T2, T3. I know that the distance from 1 to 2 is equal to the speed of light times the difference between T1 minus T2. And I guess this is absolute value, right? Yeah, this is absolute value. Eh, 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 whatever. we'll just have a negative distance. Another way to write this would be delta D is equal to C times delta T. All right, and we are looking for xs comma ys. All right. Let's go back to Desmos. So here we've got distance from 1 to 2 is equal to the square root of xs minus x1. I think having like a table or something would be nice. Squared minus the distance from ys minus y1 squared minus the square root of xs minus x2 squared minus ys minus y2 squared. All right, and then so what's known, we have this known, this is known, this is known, known, known. Maybe instead of writing it as D1, 2, I should. So we'll save that for another time. Like this isn't even a system of linear equations. So a lot of those tools for solving those is out the window, right? Do I try to approximate them using linear? Like, do I try to just approximate the hyperbola using a collection of lines rather than the hyperbola itself, right? Because I can probably approximate this red one, right? I can try to approximate the red hyperbola as y equals negative 5x plus 10 plus 12. And then y equals, well, I guess this is actually a piecewise function, right? Y equals negative. How do I do piecewise functions? Piecewise, piecewise function. I see. Okay. For x is less than 1. All right. For x is less than or equal to 2. It's this. It's this. And then for x is equal to 2, it's defined as y is just, no. Then for x is, well, no, it's not a function, right? It's not a function, so it's actually more like x is equal to, for y is less than 0, x is defined to be, if I try to, like, what is that? What would that look like? Well, as soon as you turn my brain off of, as soon as you flip my brain from x comma y to y comma x, I just break. This would be, normally this equation would look like 5x minus 12 is equal to y. So 5x minus 12 is equal to y, so x has to be equal to y plus 12 over 5, which is equal to 1/5 y plus 2.4, right? This has to be defined as 0.2 y plus 2.4, right? And then when y is between 0 is less than y is less than 2, y is defined, x is defined as just 2. No, my work. And then when y is greater than 2, we define it as the opposite of this, right? It's going to be negative plus 2.4. So this is actually not as bad. Like, I thought this approximation was going to be a lot worse than it is. You know what I'm saying? Like, I can change this to, we can change the parameters a little bit here. So like this would be y is less than -3, y is less than -1, right? We got some error, but like I can work with that. So if I can develop a way to automate these, if I can find some algorithm to like automatically develop these linear approximations, right? Because look at this. This linear approximation is crazy close. This might be the asymptote, right? How do you calculate the asymptote of a hyperbola? With the coordinate axes as asymptotes, the coordinate axes as asymptotes. Yields a new equation. Y is equal to A over X minus C. X is equal to C. Solving the equation above. Yeah, I mean, okay. This might be where I'm looking for then. So maybe I don't have to find an algorithm to do this. There might just be this. That could be cool. I think that could make sense, right? Like where I just linearly approximate approximation of hyperbolas.
In this video, I'm going to show you how to create a calculated column in Desmos in order to linearize some data to V1 insert the vertical axis values. So I'll click the, and going to 2, we now have a slope is probably
Hmm. Okay. I think I'm pretty clearly going in two directions. One where I try to solve it on my own first, and another direction where I try to read more, where I read more about hyperbolas. I think it's kind of crazy that hyperbolas have all this research and all this history behind them, and I never really found a real world application for when to use them until Now 24. Took me 24 years to find one. All right, let's spend 10 minutes. Let's just put a timer up. Timer. Let's spend 20 minutes. We'll just figure out, at least try to spend 20 minutes working on solving these equations. Trying to get them in relation to each other. Okay. Let's do that. Okay. Got all this. Solve for y. I'm gonna solve for y here. I can't just square both sides. I mean, I guess I could. Fix Epic's SSO. Database broken. They are like logins not working right now or something. Okay. So if I try squaring both of these terms, I'll end up with xs minus x1 squared minus ys minus y1 squared plus xs minus x2 squared minus ys minus y2 squared. And then we're going to be subtracting 2 times the square root of xs minus x1 squared minus ys minus y1 squared times xs minus x2 squared times the square root squared minus ys minus y2 squared. All right, so then can I do anything with this? What could I do with this? I mean, I can't isolate ys from here. Can't isolate xs either. Do I try to just not? Because, like, okay. Here, okay, so here I'm looking at the distance of the first, from the speaker to the first microphone squared is equal to xs minus x1 squared plus ys minus y1 squared, right? And then I'm looking at d2 squared is equal to xs minus x2 squared plus ys minus y2 squared, right? No, not right. Oh, these are supposed to be pluses. I don't know why I did minus. They're supposed to all be plus, 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 plus. Why did I do minus? Pythagorean theorem. Okay. And d1 comma 2 is equal to just d1 minus d2, right? That's how I defined it. It's not how I defined it. I should have. But it's also, so then d1 comma 2 squared is equal to d1 squared minus 2d1 d2 minus d2 squared. But I mean, this just gets me the exact same. This gets me the exact same equation that I'm already left with, right? Because d1 squared is just this part. This is just d1 squared. This is d2 squared. This is 2d1 d2, right? So like that doesn't help me that much. Maybe it does, and I'm just not seeing it. Like if I leave them both squared, if I leave them in the squared form, alright, so because of this, I'm always stuck with the square root. Maybe I have to do something like multiply this by d1 plus d2. Let's try that. Let's try that. So if I do d1 comma 2, no. I think my notation is also not that great, to be honest, because d1 comma 2 could mean multiple things. Anyways, not the point. Can you control V, please? Hello? Alright, we could do... My tablet just died. Hello? Alright, we're good. We could try... d1 minus d2 times d1 plus d2 to get... Do I have a... What are my shortcuts on this thing anyway? I don't even remember. We have this. What is this? What is this? What is this? Oh, this one? Control? I don't remember. Anyways, so this is going to be equal to d1 squared. What was it? d1 squared minus d2 d1 minus d2 squared. Wait, d1 squared plus d1 d2 minus d1 d2 minus d2 squared. Right? Minus d2 squared. And so that's equal to xs minus x1 squared plus ys minus y1 squared minus xs minus x2 squared plus, nope, minus, also minus ys minus y2 squared. Well, minus y2 squared. So then, how do you help us? How does this help us? How does this help us? Like, I know this. This I can know because what's it called? At a certain point, like I am very much struggling on how to solve this kind of thing for y or for x. I don't really know. But at a certain point, I just move to an easier project, right? Just so I can finish and then keep this in my mind in case I run into something, or I just keep reading about hyperbolas on the side. Because this is rough. This is rough. Like, I don't know. Maybe this says something about my tenacity if I am only 13 minutes into trying to solve this equation. It's rough. It's rough out here. Okay. Well, what else can I try? I've tried that. I know that D1 is equivalent to C times T1 minus, well, it's not just T1, it's T1 minus TS, right? And this we don't know. Meanwhile, this whole thing is equal to C times T1 minus TS minus T2 minus TS. And so this is much more easily doable because it simplifies to T1 minus T2, and then these cancel out. And we don't have the TS anymore, right? So I can only, like, this would be fine if I could figure out what if I could figure out what D2 is, but I can't as it is right now. Yeah, I mean, TDOA is just really hard. I do have this paper But this is about direction of arrival, not time. Not. What does this say? Direction of arrival. Estimation of radio relay is applicable to many cases, including localization of users. And mobile communication and radar mounted on an automobile. As an estimation method, using an array antenna, methods exploiting the eigenstructure of the correlation matrix of received signals, such as multiple signal classification, music, and estimation of signal parameters via rotation invariance, SPRIT techniques are widely known. So these are just estimation methods too. These aren't even like... Alright. In recent years, high resolution estimation methods based on compressed sensing have also been proposed. Compressed sensing is generally described as a method of estimating you're estimating an ordinal signal, which is estimating an original signal, which is given by a sparse vector. I'm glad I don't have to figure out what an ordinal signal means. Which is given by a sparse vector from fewer observations than dimensions of the signal vector. Fewer observations than dimensions. Okay. In an example of DOA estimation using compressed sensing solver called this half-quadratic regularization, higher accuracy has been reported compared with music. Okay. Nonlinear algorithms require a heavy computational load in general. Actually, HQR half-quadratic regularization needs an iterative calculation of an inverse matrix, of which dimension is the same as that of the original signal vector. So this is probably really difficult. For another nonlinear algorithm, in recent years, deep learning has been applied to various application fields. Along with the development of computer technology and its very high capability in problem solving is now widely known. Okay, so they're just tossing AI at this thing. Deep learning machine learning technique uses developed deep neural network with multiple layers and has been extensively studied in the fields of images, sounds, languages, etc. Large amount of calculations. Estimation using a neural network can be performed with simple calculation, which mainly consists of multiplication of a matrix and a vector. So what they're trying to do is they're saying training a deep neural network is a large amount of calculations, but after it's trained, getting your estimate afterwards is very simple, very easy. Thus can be said that use of a deep neural network for direction of arrival estimation is an attractive application when a heavy computational load is acceptable. We apply this to DOA estimation and evaluate the estimation performance under a scenario where two equal power and uncorrelated signals are incident on a uniform linear array. Okay. Discussion on types of training data. We consider designing a deep neural network for a specific scenario involving two close incident waves with close directions of arrival and a parallel use of multiple DNNs. Damn. Oops. I got distracted. Where was I? Okay, so they're just they're trying to specify the fit of the neural network with this problem. two close waves that are close together and they are pretty tightly packed. And parallel use of multiple neural networks designed for different scenarios. Array structure and signal arrival model configuration and training process and performance evaluation are described. All right. Oh wait, didn't I read this? I think I read another paper from this. Control H. Oh, timer's done. Okay. Control H. So we could do what was it? The paper I was reading? It was about TDOA, I think. Oops. O'Keefe. Shout outs to Brian O'Keefe. He had as a senior in college, had a pretty alright paper describing this stuff. There was a math error though, because we had this, but then for some reason in his description of TDOA, he used a minus sign in the square root instead of a plus sign. I don't know why. I'm pretty sure that is incorrect. Pretty sure, but not confident because I tried to find the paper that he sourced. This one. Trying to find the paper that he sourced. Wireless communication, networking, and applications. Oh, no, not the same journal. I tried to find this paper, but 4 of the pages were blocked that went into the math. So, oh well. Hello. Hi, Riffmock. Okay. So, I don't need this anymore. I think for the sake of my sanity, I'm going to swap to a simpler problem. I'm going to save this project. I'm going to save this for now. Until I can figure out how to solve these equations. I don't know. Like the directions I can go in are either A, read more on hyperbolas. B, linearly approximate solutions. Man, my handwriting is not good on these tablets. C. What is C? Is there a C? I don't know if there's a C, to be honest. Read more on hyperbolas, linearly approximate our solutions, or I don't know. C. Move on. For now, I'm gonna go ahead and pick C. So next time I stream, I'm gonna swap away from the TDOA method and instead go over to a, oh, nope, I want this. I'm gonna stray away from the TDOA method and instead move on to the time of arrival method. So let's get a new blank graph. So in that one, much simpler. I just go x1 comma y1 for my first microphone, x2 comma y2 for my second microphone, x3 comma y3 for my third microphone. Can I get a folder? Put all this in here. How do I mic 1. Copy all these. Jam them all in here. Delete this. Let's put this microphone over here, put this microphone over here, put this microphone over here, whatever. Folder within folders. Microphones. Bam. 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 Wait, no. Shoot. I need another folder. Mic 2. Bam. 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 I don't know why I'm putting this so much effort into Desmos product, to be honest. It's more effort than I'm putting in the actual like Arduino coding. Can I not put folders in folders? All right, I guess not. In that case, oh well. Bam, bam, bam. This is mic 3. Okay, so we've got all these mics. Mic 1 is going to be at the origin. Bam, bam. Mic 2, we'll put it, let's put it at like 3, 0, something like that. And then the microphone 3 will be at 2, 5 or 5. Sure. 5. Okay, with TDOA, with the time of arrival method, we already know when the speaker sends out the sound, so it's much easier to calculate the distances and figure out where the speaker is placed. So for example, here we've got, let's say, so we know that the speed of sound is 346 meters per second. Speed of sound in air is 346 meters per second. Let's say that time 0 is equal to 0. Time 1 is equal to, so we know when the speaker plays. By the time it reaches microphone 1, let's label all these. By the time it reaches microphone 1, let's say it took, I don't know, 0.01 seconds, right? Let's label this microphone as well, mic 2, mic 3. All right, so this is the time it takes the sound to go from the speaker to microphone 1. So then distance 1 has to be equal to C times the difference between T1 and T0, right? And so this is the distance between the speaker and the first microphone. And if I do D1 squared, right? If I try to use Pythagorean theorem, I can find that the first microphone, the x direction, x minus x1 squared plus y minus y1 squared. It's going to get this circle of all of our possible solutions. So this is where the speaker could be. Mic 2, let's say, takes let's say T2 is equal to 0.02. I actually don't know. 2. T2 is equal to C times T2 minus T0. So then in this case, mic 2 has to be this much further away. 3.46 away, so it has to be 3.46 over here. Okay. And then we've got D2 squared. So now I'm trying to figure out, in relation to mic 2, where is the speaker? It has to be x minus x2 squared plus y minus y2 squared. And we can see it makes this circle. This is all the places where the speaker can be. If I overlap it with this mic, we see that they overlap in exactly one spot. Cool. Cool. And then let's say if we change the position. Let's see. So this tells me that the speaker's over here. What is the distance? Let's see. Mic 2, mic 3. Let's add a new folder. Speaker is going to be located at X, oops. What was it? XS, comma YS. Let's say the speaker is over here. -3.46, comma 0. So this is where the speaker is. Let's change the color real quick. And let's label it as the speaker. T0, T1 is going to be the distance. Okay, so the time that it takes to go from speaker to mic 1 is going to be the distance divided by the speed. So the distance is going to be square root we got the square root of s minus x1 squared plus the distance between them. Oh, right. Why am I tripping so much? Man, I am rusty. I'm rusty with this stuff. Squared. It's all going to be divided by c. So t1 is going to be 0.1. Plus t0. So then if this goes up, this also goes up. All right. And then the same thing is going to follow for T2. When we have XS, but this one's going to be 2, Y2. And then the same thing is going to follow for, oh wait, it's T2. T3. Okay. All right. Man, this is a lot. These are a lot of little, what's it called? A lot of lines. Well, I guess that's what it takes to get an accurate depiction of this. I don't know. I might also just be going extra because I feel like being overboard. All right, so we got 3 values. Okay. Normally, the speaker is hidden away from us. And then, so we've got this, and then D3 is going to be equal to the same thing. T3 minus T0. All right. And then we'll do the same thing here. D3 squared is equal to all of this, but for the third mic. Okay. And if I just move the speaker around, let's say that the speaker is over here. Okay. All right. So, speaker's in some hidden location, some location that we don't know. But we do know when it sends out a signal. And we also know that this is a constant. I don't need this to be, what's it called? I don't need this to be a slider. All right. This is the speed of sound in air. This is the time when the speaker sends out the signal. And so it's going to travel some distance, right? And then that time that it takes, plus the original time, that's going to be the time it takes to hit microphone 1. So microphone 1, it hits it in this amount of time. Microphone 1 picks that up and it says, okay, this is how long it took. Based on that, we can calculate the distance the microphone is away from the speaker. And it's going to be 8.7 whatever, right? So we're looking for all the points where the distance between the microphone and the speaker is 8.7. And that'll give us this big old circle. Let's do this in red. Do this one in red. Do this one in blue. No, this one in purple. This one in blue. I'll turn these off. Okay. Same process happens for microphone 2, where we figure out, okay, this is the time that the microphone reads the clap happening at. And it says, okay, based on that, we're going to multiply it by the speed of sound, and we'll get this. Now we're going to look for all the points where this is, what's it called? We're going to look for all the points where this is the distance. This is the distance from the microphone. And we'll see, okay, we've already got a solution, actually. Oh, hold on. We don't actually have one solution. We have, if we zoom all the way in, we have 2 possible solutions. So the microphone could be here or it could be here. We're not sure. One of those 2 spots. One of those 2 spots. So let's get a third microphone in. We'll do the same exact process. And by this time, if we draw another circle, there's only one possible solution. All right, so there's this intersection between the green and the purple, and the purple and the red, and the blue and the red, but and this one for the blue and the red, but none of those matter, because what I'm looking for is where all 3 intersect, and that's going to be at this point right here. And if you go back to where the speaker is, if I actually show you where the speaker is, it's right at that intersection point, and that's not a coincidence, right? And so ideally, if I don't have the speaker, I'm going to be able to do calculations from this, and this on my little board. So I'll have a little board that has 3 microphones on it. And then I'm going to calculate the distances from the speaker, and then try to solve these 3 equations. Now I got to figure out how to solve these 3 equations, which is, I think, easier, but not necessarily. I think it is easier. It is easier. I just got to figure out how to actually do it. Because for here, if I look at this is going to be y is equal to the square root of d1 squared minus the x distance, x minus x1 squared, and then add y1 on top of it. If I do this in all right, so I'm going to solve this, and at the same time I'm going to solve for this, and at the same time I'm going to solve for this. This one's going to be d2, be d3, x3, y3. I feel like I messed up somewhere. I've definitely messed up somewhere. I'm just not sure where. We subtracted this. 2 squared, took the square root, and then added the y2. Yep. Nope. Okay. I did not mess up. That seems. But, oh, I see. I see the problem. Okay. This is on the bottom portion of it. The bottom portion of the circle. That's why it's not showing up. Okay. So I gotta figure out. So then this one is negative y. Nope. Minus y3? Nope. Plus y3. The negative root. Okay. So the intersection of all 3 of these is going to be our same speaker spot. How do I solve them simultaneously? How do I solve them? I have this. I say that this part is equal to this part. I subtract y1 minus y2. Try to solve for x. Okay. Yeah, okay. So from here, I try to, that turned off. Okay. So from here, I try to do y, nope. Try to do some black. Square root of d1 squared minus x1 squared plus y1. And this will be plus or minus. Ah, shoot, that is plus or minus, huh? Oh well. Okay, let's see what happens first. Let's see what happens first. Let's set that equal to this one, d2 squared minus x2 squared. Solve that square root plus y2. And then we'll try to do wait, this does get messy very fast. This gets messy very, very fast. Instead, let's try, I don't know. Let's see. Solving for intersection of 2 circles. Okay. Given the radius, how can I calculate their points of interest without any trig at all? Okay, by subtracting 2 from 1 and expanding, we get a linear equation. Oh, nice. Okay, well, I'm going to use the bathroom, and then I'm going to read this. This is promising, and I'm pretty sure I probably learned about this in high school and just forgot. So, uh, there are all of these great answers. A lot of these are great answers. But what we're looking for right now is we've got this. So if I subtract this, so this equation minus this equation, I'll end up with negative 2 times, and then we expand as well. We'll end up with x minus x1 squared, that's x squared minus x1 squared, x squared minus 2x x1 squared minus x1 squared, or plus x1 squared plus x1 squared. We end up with this minus this squared minus this squared. We end up with x1 squared minus this x2 squared. We end up subtracting the y1 squared minus the y2 squared. Wait, that doesn't seem right. Hang on. Why are we doing? So we have. Oh, right, because we're subtracting that. Yeah, we're subtracting. We're subtracting this equation and this equation. All right, so we'll end up with this. Then we'll end up with if I'm just solving for y, I'm gonna add this on both sides. We'll end up with 2x times x1 minus x2 times all of this. No, plus all of this. And then we divide by 2 everywhere, so we end up with just the x times x1 minus x2. And that's going to be negative because we're divided by negative 2. And then we'll divide everything by y1 minus y2. Okay. So then, from there, I'll be able to solve for x, assuming that y1 and y2 are not the same. Okay. All right. Okay, what's another way? And focus on the center point of both circles. Okay. So it's like you have two circles. You have two circles intersecting each other. And then you take a plane that cuts through both centers. So these, you got the two centers, and then you just have a plane that cuts through them. Okay. The distance between the centers of the circles is given by that. Yep, that's just Pythagorean theorem and all that. And then we consider these vectors. A is the vector from the first center to the second center divided by the distance. So it's just length of 1. B is is just perpendicular to it. Okay, sure. In the AB plane, we get the equations A plus R over 2 squared plus B squared. So A plus the radius plus half the radius, because it's halfway between already, squared plus B squared. Okay, so we just rewrite the equations of a circle. Yeah. I'm not reading all that, but I believe you. The intersection points are given by x and y. What the heck, man? Or some JavaScript script code that. All right. Intersection points are given by 1/2 of. Okay, yep. You add the 2 points together, halfway between them. Subtract the radii squared, divide by 2r. R represented what again? The distance between the centers? Sure, dog. I don't know, man. Okay. So when one point is on the origin, another point lies somewhere on the x-axis. So we got 0, 0. We got d0. We got the radii. 2 equations simplify to that. Yep. Equations of a circle. Equation of circle offset by this d. So it's equation same equation of a circle, different radius, and offset by some value d. All right. Use the first to find y squared. And then substitute into your second. Okay, so y squared here is going to be r1 squared minus x2, x squared. To end up with that. Yep. Expand and simplify. You'll end up with this minus 2x times d plus d squared plus this. Okay, and then these two will cancel out. Is equal to that. So then x is going to be equal to this. X is going to be equal to r2 squared minus r. Yeah, okay. r2 squared minus r1 squared minus d squared, but divided by negative 2 times d. So then you just make the minus sign and you do this. Okay. Okay. So then you've got x is that. These are all numbers, so you can calculate that. And then from Pythagoras, you know that we basically just did, so this part, we just solved for this. We said r1 squared, subtract it by the x squared, and then take the square root of it. You get this. For the general position case with points x1 and x2, we do similar process, I guess. I'm guessing it's a similar process. Okay, it's a similar process, but they're generalizing it, yeah. L is equal to that. L is equal to this. Okay, so you get the same solution, but you need to account for the fact that D, so like, you're just changing your perspective to make it so that they're still in line, but you have to account for that when you go back to the regular XY plane. Our two orthogonal unit vectors, then we can rotate and translate to get the general solution. And so then this becomes similar to this, I think. All right. Okay, so there's multiple ways to do it. But it seems like it's still way easier than hyperbolas. All right. Cool. Good stuff. I think I can close out of this. Oh, let's save this actually. TOA solving for TOA or trilateration using TOA. Got this. Okay. Very cool. And then if I change where the speaker is, everything else is going to automatically adjust for it. The only thing I have to account for is that when we get to the bottom section of the circle, then things get messy. All right. Let's turn these off, turn these back on. You'll notice that no matter where the speaker moves, we can still calculate our 3 circles and find the intersection point, no matter what. And I think that's pretty beautiful. Okay, so I'm gonna swap to a TOA approach, but to be honest, I'm probably gonna start with just an echo, like detecting a wall, and that's it. Because I am now I'm 2.5 hours into this, just this session of research. Hyperbolas, you're gonna have to wait. All right, I'm just not ready for this right now. I want to at least have something done. At least say I finished it. You know what I'm saying? So, all right, we got this. Let's close this timer. Thank you for anybody who tuned in. Thank you for anybody who watched through it. I know that this is a pretty heavy math thing, and to be honest, some of it's kind of. I know there are people out there who will say that this is basic math, and it might be, but it's still pretty cool to see how these things come about from just trying to solve a problem of where is a speaker. So, yeah. Thanks to everybody for watching, and I